use the formula, the addition formula essentially, to prove that tan 90 minus theta is cot theta. So I'm going to want to use tan A minus B. I'm just going to focus on that one instead of the pluses, because then I can let in a minute A equal 90 and B equal theta. So we'll get sine A minus B over cos A minus B. And then technically these are identities. And then I'm going to apply the addition formula for each one. So sine A minus B is sine A cos B minus sine B cos A. And for cos, we get cos A cos B. In this case, it's plus sine A sine B. All right, nice. So I'm going to let A equal 90, like I said, and B equal theta. So I'm going to need to substitute in for 90 at some point. I'm going to get sine theta and cos theta, obviously, but I'm also going to get sine 90, which is actually 1, and cos 90, which is 0. So this is going to help simplify things a lot. Therefore, tan 90 minus theta is going to equal sine 90 cos theta minus sine theta cos 90. Straight away, I can just cross that one out, by the way, because we've got that cos 90 is 0. And then dividing by cos 90 cos theta plus sine 90 sine theta. So again, I can just cancel that one out. Sine 90 is also 1, so I can just cancel them out, leaving me cos theta over sine theta, which is cot theta, as required. On to part B, which is to solve this equation, but you've got to be thinking that this result from part A is going to be useful, going to make life easier. Turns out you can do it without using that result, but it ends up being a lot more complicated. Now, the odd one out here really is the tan theta minus 34. We've got theta plus 11 for the other two. So if I could somehow convert this theta minus 34, maybe that will work. I've also got a sec squared, which I need to get in terms of tan squared. But when I did it, I thought, right, the first thing I'm going to do is look into this tan theta minus 34. Can I write it in the form tan 90 minus theta? Tan of 90 minus. Now to get minus 34, I'll do 124 here. That will then give me minus 34. And if I put a minus theta in here, then that checks out. And so it's now in the right form, but the theta here is actually my 124 minus theta. So I'm going to get cot of 124 minus theta. Now, when I did it, I kind of thought, you know what, I'm making this more complicated. How is this going to help? But just stick with it and let's try and use some other identities. Because another thing jumping at us is the fact that we've got sec squared. We want to maybe get that in terms of tan. So let's use the fact that sine squared plus cos squared is identical to 1. Divide through by cos squared. Tan squared plus 1 is identical to sec squared. So I can replace all of this by tan squared plus 1, which is going to end up giving me 2 minus tan squared theta plus 11, and then a minus 1. And that is going to equal 2 tan theta plus 11 multiplied either by that tan theta minus 34, if you're not quite trusting that the cot is going to help, or put the cot in. Okay, that's the bit that maybe might be unsure about at the moment. Because it turns out over here we end up with a difference of two squares. 1 minus tan squared theta plus 11 equals 2 tan theta plus 11. Okay, the thing is, If you factorize this, it doesn't really help with the right-hand side. So let's not do that for the moment. In fact, there's a formula going on here that you have to kind of think about carefully. If we divide through by 1 minus tan squared, in fact, we get the double angle formula for tan. Let me just write that down. Because tan 2a is actually equal to 2 tan a over 1 minus tan squared a. So you can identify that, then you're on to a winner. We just need to rearrange this. I'm going to get 2 tan, in this case, theta plus 11, that is my a, divided by 1 minus tan squared theta plus 11. And that is going to equal tan of 124 minus theta, because I've got this over to the other side. I've timed through by tan 124 minus theta. Now it makes sense why we've used this, because everything is in terms of tan. So tan times 2 lots of theta plus 11, that's my a, like I said, is going to equal tan 124 minus theta. One clue in the question was that all the answers are actually going to be integers. And this is great, we don't actually have to do inverse tan. One solution would be to simply set the bits inside equal to one another. So 2 theta plus 11 equals 124 minus theta. So 3 theta is equal to 100 and... Oh, sorry, I made a little mistake. Just spotted it. I forgot to expand the bracket here. It's going to be 22. Apologies. Okay, so 3 theta is equal to 102. Divide through by 3, we get 34. That is a solution. Now, there's more solutions because you've got to think about how tan of this can equal tan of this. They're also equal if there's no symmetry rules for tan in the same way, like, well, there are symmetry rules, but not when they're all positive, like so what I mean is sine x is equal to sine 180 minus x. You have to consider these possibilities, but for tan, it's just we add 180 on to get another solution. So in fact, we could write down, I can see if I minus 180 from the right-hand side, I'm going to end up with a negative, so I don't need to consider that. But I can say that 2 theta plus 22 is going to equal 124 minus theta plus 180, or plus any amount of 180. K is an integer. Technically, we could say that k belongs to the set of integers. Now if I rearrange this, I get very similar. 3 theta equals 102 but plus 180k. And when I divide through by 3, I get theta is 34 plus 60k. So now I just need to cycle through the different values of k. So if k is minus 1, we get a negative. That's not in our range because we're only interested in 0 to 360. So if k is 0, I get that 34 I got before. K is 1, then I'm going to get 94, and it's just going up by 60s every time. Then 154, then 214, 274, 334, then it'd be 394, which is outside the range. So I'm hoping you've seen something like this before. It does come up on AEA papers. It's a little bit confusing the first time you see it, the fact that you've got tan of something equal to tan of something. But just like you would with if you had, say, 2 to the x plus 1 equals 2 to the 4, you would automatically say x plus 1 can equal 4. It's same here, but you have to remember the periodicity of the trig functions. And in this case, for tan, it's going to be true if we add 180 on. Of course, you could add 180 onto the left-hand side instead, but then it would just be minus 180k, and then you'd look at the negatives, for example. So you don't need to consider that one as well. We can just add it to one side and then vary the multiples. So that is a really nice way of doing this question. Look how quick that is. So, you might not see it straight away, but you got to be thinking about the identities to use. Get that sec squared identity in there. although we've got a difference of two squares, actually what the hardest bit is spotting the double angle formula going on. Once you've got that, and it all just works out really nicely after you convert that tan theta minus 34. And you might not do that straight away, to be fair, but hopefully you'd realize at some point you're going to end up with tan equal to cot, and then you're going to have to swap it round. Anyway, that's a really nice way of doing this question. Right, here is a less nice way of doing this question, but it does get the job done. Okay, because you might be thinking, I never thought of doing that. And it's always good to talk about alternatives, even when they're not as good. It's not always, let's just talk about the best solution. Sometimes we get a bit of insight from other methods as well. So one thing I spotted when I did this question, because I actually ended up doing it this way, I kind of I made progress with this, and then I didn't spot the double angle formula, and I went down a different path and got the right answer, but then in hindsight saw that I could use the double angle formula. But what I noticed is that 11 and minus 34 differ by 45 degrees, and 45 degrees is a key trig value because we know that tan 45 is equal to 1. So I decided to convert this and think about what happens when I've got tan A minus 45. Because actually I could write this as tan theta plus 11 minus 45. That's where I'm coming from with this. So in a minute, I can set A equal to theta plus 11. Okay, so our formula is tan A minus tan 45 all over 1 plus tan A tan 45, which becomes tan A minus 1 over 1 plus tan A. And that means that tan theta minus 34, sorry, not tan theta minus 34. I'm going to let's A equal theta plus 11. That's what I meant. So um, tan of theta minus 34, sorry, I've already let A equal. That's going to equal tan theta plus 11 minus 1 over 1 plus tan. You can already see this is getting more complicated because we've got a fraction. I then did exactly the same thing by getting this in terms of tan. So we're going to have 1 minus tan squared theta plus 11. I've already shown where that's come from. And then it's going to equal 2 tan theta plus 11 multiplied by this thing that we've just found. Sorry, I didn't leave enough space there. Just going to write that out again. Okay, and then this is where the difference of two squares came in useful. Because I can write this as 1 plus tan, and do you know what? At this point, I'm just going to call it tan x. X can equal theta plus 11. To be fair, I could have called it A, but let's call it X because that's what we're trying to solve for. Then 1 minus tan X is going to equal 2 tan X times tan X minus 1. But what we see is we've got 1 minus tan X over here. So if I times by minus 1 and minus 1 up here, I can write it as 1 minus tan X. They're the same thing because I've got a minus times 1 minus tan X. That takes us back to tan X minus 1. And the reason I've done that is that now I can cancel these two out. Except I need to include the fact that it could equal 0. So tan x equals 1, or 1 plus tan x equals minus 2 tan x over 1 plus tan x. So I'm kind of not going to just cross it out, actually. I need to consider the case when it's 0, but that's what I've done. So when it's not 0, I can cancel it out. When it is 0, I've got tan x equals 1. Therefore, x is 45 degrees, or adding 180, also 225 degrees. Now, don't forget, though, that is theta plus 11. So theta would equal 34, or 214. So those are two solutions. And they are two of the solutions that we had earlier, 34 and 214. We just got the other 4 to obtain. Okay. Right. Now we've got this left over. So what I'm going to do is multiply through and make it 1 plus tan x all squared equals minus 2 tan x. Expand the bracket, tan squared x plus 2 tan x plus 1 is equal to minus 2 tan x. And I've got myself a quadratic for tan. The thing is, I know that I've got whole number solutions, but I don't have many exact trig values, and we're going to find out in a minute that we get into a little bit of a difficulty, which is probably the main reason for not doing this method. Actually, the main reason is just quite long, but the second reason, because this does not factorize. The other one did, but there's no way this will now. You can either use a quadratic formula, or we could complete the square in terms of tan x. So it would be tan x plus 2 squared. That'll give us tan squared x plus 4 tan x. Then I would need to minus 4 and add 1, get 0, which means tan x plus 2 all squared is going to equal 3. I take the square roots, then I get plus or minus square root of 3. So tan x is going to equal minus 2 plus or minus square root of 3. Now we know that this is going to, well, assuming we trust ourselves that we've done it correctly, we know this is going to give us an integer solution. Don't forget, this is actually theta plus 11. I might put it back in just so we don't forget about it. So it's none of the exact trig values that we know. You might recognize it if you've done other AEA questions or potentially even A-level questions, but let's assume not. All we can really do is find some more like fairly nice exact trig values. And one would be, say, tan 15 degrees. You can see why this is just long and unnecessary, really, when you compare it with the first solution. So we could find tan of 15 by doing tan of 45 minus 30 and applying the addition formulae. So it'd be tan 45 and then minus tan 30 all over, I think it's 1 plus tan 45 tan 30. So this is 1 minus 1 over root 3 over 1 plus 1 times 1 over root 3. Times top and bottom by root 3 to get rid of the fractions within fractions. Root 3 minus 1 over root 3 plus 1. Times top and bottom by root 3 minus 1 to rationalize the denominator. It's going to give me 3 plus 1 minus 2 root 3. On the bottom, 3 minus 1, so 2. That is 4 minus 2 root 3 over 2, which gives me 2 minus root 3. Okay, now I don't actually have that. I've got minus 2 plus root 3, or minus 2 minus root 3. But I nearly have it, and actually tan of minus 15 would be the negative of this. It would be minus 2 plus root 3. So that will work I don't want a negative, but if I add on 180, then I'm going to get 165. If I add on 180 again, I'm going to get tan of 345. So that's it. X can equal 165 or 345. Remember, this is theta plus 11. So we get two solutions. Theta is going to be 154 or 334 degrees. Okay, we've still got more to do though, because we've got that negative one to deal with, -2 minus root 3. So we've done 15. The kind of next step is to realize you've got to do 75. So tan 75 is going to be tan, let's go with 30 plus 45. So tan 45 plus tan 30 all over 1 minus tan 45 tan 30. 1 plus 1 over root 3 again, this time over 1 minus 1 over root 3. Which is root 3 plus 1 over root 3 minus 1 times by root 3 plus 1 over root 3 plus 1, which gives 3 plus 1 plus 2 root 3 all over 2. 4 plus 2 root 3 over 2 gives 2 plus root 3. And again, I haven't quite got it, but I've got the negative of what I want. So tan of minus 75 would equal -2 minus root 3. Or I can add 180 on. So tan of 105 or tan of 285. Again, that's theta plus 11. So theta is going to be 94 degrees or 274 degrees. Oh, okay, that took a long time, but we made it work. Okay, it's not as good, but it's quite interesting how it's just a completely different approach. The problem is getting that value, and we avoid it with the double angle formula because of how it all works out. Anyway, this is a nice question. I enjoyed it. It's a little bit different. And I've seen questions on AEA where you get results like this, and there's a lot more to consider. But here with tan, it actually works out really nicely. Um, so yeah, thanks for watching, and well done on this question.